Hello, Rohan. Am I audible?
Uh, Yes, sir. Yes.
Okay. So, why do you pursue PhD from?
Sir, St. Xavier's College, Kolkata. I live in Kolkata also, sir.
Okay. So, have you given the JAM IIT-JAM exams?
Yes, yes, yes.
So, what's your rank?
Sir, 55. AIR 55.
Okay, nice. So, are you? I mean, what's your main purpose for doing Masters of Statistics? Like, it's PhD or just job?
No, I won a PhD in theoretical statistics, so that's why want
Oh,
to get
you
into ISI.
okay. So, do you know about probability integral transformation?
So, that means, basically, for any distribution, the CDF follows uniform 0, 1. That is what it means by probability integral transformation. Um,
Yes, I am asking you the question. So, what you have said, are you sure about that?
yeah. I
So,
mean,
like x be a random variable with. So, what are you saying? I mean,
if x is a continuous random variable with absolutely continuous CDF f, then it should f is should follow uniform 0, 1.
can you
So
prove this? It is right, completely right. But can you prove this? It is 2 or 3 line proof.
okay, okay,
I mean, you love theoretical statistics, so I like to question you from first the question from that.
okay. I am opening the whiteboard.
Yes, yes.
Is it visible?
Yes.
Okay, say x is a
Okay, okay. I mean,
continuous.
you don't have to write all those things. Just do the proof.
Okay, okay. Let y is f of x, another variable denoting the distribution function, and
Yes.
then probability capital Y less than small y is same as f of x less than small y. Now, here I am using the fact that if x is absolutely continuous and non-decreasing, then it will have an inverse. So,
Very good. Then
if x less than equals to f inverse y, now then it is f of f inverse y, which is simply y. So, CDF of y is uh,
so
y,
the
and the range is
so the
in between 0 to
yes,
1.
yes,
So
yes.
that
You
means
have to write this.
okay, okay, okay.
If y less or equal to 0, then what will it will be?
It should be 0,
It
right?
will
Because
be yes, yes. And
because
if y greater or equal to 1,
it will be 1.
okay, very good. So
That is
now
why
tell
y
me,
capital.
have you? I think you love theoretical statistics portion. So tell me, uh, the intuitive. You know the Markov's inequality and Chebyshev's inequality, right?
Yeah.
So you know the expression, all those stuff. I will not ask you those things because I know you know. But tell me the idea. I mean, the distinguish the idea between Markov's inequality and Chebyshev inequality. Without, I mean, you can write the expression and say to me that you can write the expression also. But
Okay,
I am
okay.
saying you the say me the tell me the idea behind those.
Why should we use those inequalities and something
Yes,
like that?
yes, yes. Right, like those. Just tell me the idea why we require those. I mean, and what's the difference between those? Just you tell me the idea. Don't you can write the expression
Okay,
also. I am not telling you to write, but you can write.
okay, okay.
Just tell me the idea.
I mean, this is the Markov inequality if x is a non-negative random variable. Now, uh, basically, we used to give an upper bound to the to those type of probabilities which are not easily computable. I mean, I think
Okay.
that is the main reason to use Markov and using Chebyshev's inequality, which is simply probability of mod of x minus expectation of x, which is sorry,
Suppose the expectation of x is mu.
okay, okay, mu and greater than k is less than equals to variance of x. I am assuming sigma square
Was
upon
squared, yes.
k square. Now, basically, these are the application in SQC. Like if we can show that the probability mod of x minus mu, if we take k is equal to 3 and sigma square equals to 1, and then we can show that 99.97% of the points lie in
Yes,
this.
I mean you are saying correctly. I mean I am not saying you are wrong. Okay, one thing, just one thing. When you write those expressions, you have to be precise. One thing that what you have to write also. I mean when this expression holds, you have to write that expectation of x is finite, right? Otherwise, it
Right, right,
cannot
right.
hold. Those stuffs
Right.
you have to write. Okay, so be aware of that.
Okay,
Okay.
okay.
So, whatever you have told about the idea is correct. It's not wrong, but I want I want to hear the precise thing. Okay. So, I am asking you, just think about that. Don't be stressed. Just think you are going in right direction. You are giving an example. Uh, I am not asking you the example. Just think about the example and what's the idea regarding that. You have given the example of Chebyshev inequality, right? You have right.
Yeah.
You are absolutely right. So just give me the exam. I mean, give me the idea regarding that.
I think it denotes the concentration of the random variable uh, with respect to mu. I mean, the mean. How much is it?
Yes.
How much is it constant? It denotes the variation, right? How much
Yes.
the values will
Concentration
be?
is the right word. Okay.
How much it
Concentration
will
is the
be?
right word.
Okay. Okay. Okay.
I mean, regarding the concentration of the distribution on an interval, right? It is an interval. You are taking the concentration in that with the
Yeah.
midpoint of mu, right?
Right.
Using
Right.
the
Right.
variance of the distribution. It is
Yes. Yes. Yes.
Chebyshev inequality's idea and the Markov's inequality idea. You have told some. You have, I mean, you misjudged a thing. Like it provides the idea. I'm telling you, it provides the idea regarding the tails probability of the distribution using the mean. Yes, you want to check the tail part. So you are writing greater equal to c, and you are want to check the probability of the tail portion, and you want to bound that. So how can you do that? You want to check those things. You want to check
Okay. Okay.
the tails probability portion. Are you getting my point?
Yes. 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 I mean, if C is
Okay.
very large, then what will be the probability of x greater than equal to?
So so you are asking your, I mean,
No, no, I'm confirming like that, man. That those are the tail probabilities, right?
yes, yes, yes. So I mean, it should be like if you goes to it should be zero, right? Because you are going
Yeah,
to
yeah,
infinity portion.
yeah.
So how can those be in probability like this? Okay, so one question. Okay, listen very carefully. This question. Okay, consider four positive numbers. Okay, four positive numbers such that their sum is 2025.
Okay,
If the numbers are chosen to maximize their product, Then what is the value of, so you can write uh, thing, I would consider four positive numbers such that their sum is 2025. Then if the numbers are so chosen to maximize their product,
To maximize their product, right?
yes, then what is the value of, I am telling you the value.
Okay.
Okay, so the value of AM by GM,
M upon GM,
yes, plus GM upon AM
GM upon AM,
plus second bracket start AM plus GM times 2. I mean, just take the bracket, first bracket AM plus GM bracket close, and times 2. So what will be the value?
now if we consider those numbers as x1, x2, x3 and x4, now then if we apply AMGM here, then this AM is greater than equals to whole to the power 1 by 4. And now this sum is 2025, and now the maximum value should be 2025 upon 4 whole to the power 4. So the product is this, and
So when the product will be maximized?
so if we take all four numbers as this quantity divided by 4, then if that means if we take AM equal to GM, I think then will be the product will maximize.
Yes. So what will, when it will be? I mean, equality also when?
Equality when, so when all the xi's are same, I mean is equal.
Okay, so do that.
Okay, so each and every xi should be 2025 by 4 whole to the power 4 divided by 4, and for all I.
No, you are missing that. So like, I mean, you have to. I mean, AM equals to GM, right?
Right, right.
So do you
Oh, no,
need
no.
anything? I mean, any XI value or like those? Because I have asked you the final value. So why do you need the individual value of that?
No, no, actually, I do not need the individual values. So in this
Yes.
expression, if we put AM equal to GM, then this quantity will be 1. Uh, this is also 1. This is 1 plus 1, 2 into 2, 4. So I think this is 6.
So AM plus GM, it will be 2. I mean, AM equal to 1. Are you sure?
No, 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 no,
Or
no, no.
GM?
Sorry, 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 sorry. No, no, not AM equal to 1. Let me. AM will be 2025 by 4. So, uh, so 2025 divided by 4. Now, if GM is also 1, we can write it again into 2, and there is a into 2 in the outside. So 1 plus 1 plus 2025, 2027.
Yes, very good.
2027.
So Rohan, this is from my side. Have a good
Okay, sir.
interview. I think you will give a good interview. Best wishes for you.
Thank you, sir.
Showard will take over.
Okay. Am I audible? Hello?
Yes, yes, yes. Yes, sir.
Okay. Fine. So, what has been your most favorite topic in this 3 years?
Something along the lines, statistical inference and regression, maybe. Not that much, but inference mainly.
Except inference because that's the part everyone does. Except inference. You said you
Then
like
maybe,
theoretical stat.
yeah, then maybe regression.
Okay. Uh, can you just write the linear regression model with the appropriate assumption?
Okay, say simple linear regression model, right?
Yeah, simple.
Okay, say,
You can take p equals 2, like two of the covariates.
okay, okay. So y is the response and x is the predictor. And so we have n data points. So mainly the model is y equals to alpha plus beta xi plus epsilon I uh, for all I equals to 1 to n. And the assumptions on epsilon I is that first of all, expectation of epsilon I should be 0 for all I, and the zero mean assumption. Then variance of epsilon I should be fixed, the homoscedasticity assumption. And finally, covariance of epsilon I comma epsilon j should be 0 for all I not equal to j, the uncorrelatedness assumption. So now in matrix form, we can write this as
I do not know. I do not need the matrix. Only these are the assumptions, right?
uh, initially these are, then I think there's one more assumption that xi should be uncorrelated with epsilon I. I mean,
Okay. Like, yeah, is there no distributional assumption?
for OLS, I think there is not any distribution assumption, but for deriving the maximum likelihood estimators, we take the Gaussian and normal distribution to be the distribution of epsilon I.
Okay, good. Okay, so now think of a particular situation. Okay, like you are working with a real life data set. Uh, when can you provide a situation that we may tend to select a gamma distributed error, like a distribution of error instead of selecting normal, we are selecting gamma. Is there any situation?
Uh, distribution. Okay. Now the basically the response gets this distribution from the epsilon i's because we take x as non-stochastic. So if the response is somehow skewed in positively skewed in nature, so we can take gamma distribution as the distribution of errors. I mean, if it's not symmetric.
Yeah. Good.
Uh, Now real life example is
No, it's fine. Uh, okay. Um, what is you have read about type 1, type 2 error, right?
yeah,
Which one is most severe according to you?
type 1 error. Now
Why?
okay, okay.
Like you are sure that type 1 error is severe? First tell me that,
I mean, it basically depends on the situation, right? I mean,
right?
type 1 error is basically the probability of rejecting the null hypothesis when it is actually true. Now, again, in the classic example of a courtroom scenario where we should not punish any innocent person. So, assuming that the null hypothesis is that he is innocent, so here maybe type 1 error is more severe, but in some cases, type 2 error may be also more brutal than type 1 error. But
So it depends on the situation, right?
right, right.
Like you cannot actually say that
Which
type
one is
1 is more severe.
okay? Okay.
Always. It completely depends. For example, the common, uh, you said you have read in St. Xavier's College, right?
Yeah, yeah.
So the most common example that we are given is that criminal justice one, right?
Right, right, right.
So we are made to think from the point of view of the victim or the
Victim.
one who is providing the justice, right? In that
Right, right.
case, we say that it's type 1 error, which is more severe.
Yes.
But what if you think in the from the perspective of the person who has been on the trial, like the person who has committed the murder? You are a statistician. Your work is not to judge between who is the murderer or who is the victim. That's the work of the lawyer. But if he is a human being, the victim is also a human being. So if you judge from his perspective, then type 2 error is much more severe, right?
Right. Actually, yes, yes, yes.
Okay, fine. Hmm. So, what is can you define the weak law of large number?
The WLM. Okay, fine.
Yeah,
It, hmm. So, xn is a sequence of random variables. Variables and which are IID. I mean, independently and identically distributed. Then, if we define Sn as summation over k equals to 1 to up to n xk, uh, then Sn upon n goes in probability to mu, which is when now where mu is the expectation of xi. I mean, this is the I think this is the simplest form of WLM.
simplest form. Yeah, okay, that's right. So, any idea about strong law?
Stronger than no, sir, no.
Okay,
Sir.
fine. Okay. Now, okay, suppose let us come to a question on multivariate. Suppose sigma is given as a variance covariance matrix, which is positive definite.
Okay.
So, now can you find uh, a non-trivial upper bound of, uh, I'm asking for a non-trivial one, probability
Probability.
x minus mu transpose,
Oh, okay. Only x minus mu transpose. Right.
not only x minus, let me just give a bracket here, sigma inverse x minus mu greater than lambda Yeah, I want the non-trivial upper bound of this quantity where lambda is greater than
Lambda is greater than
0.
oh 0. Okay, okay. Non-trivial upper bound. Zero. I mean, is this for any distribution or uh,
You
normal?
can
No, multivariate normal, right?
assume multivariate normal. I think the assumption won't be needed. Okay, you can proceed to multivariate.
Okay, okay. So, say X curl follows uh, multivariate normal, p variate normal with mu curl comma sigma. I mean, now if I look at this quantity, the x minus mu transpose sigma inverse x minus mu, this thing is a scalar. So basically, this is a p, 1 cross p, this is p cross p, and again this is p cross 1. So this is a scalar quantity. Now let this is y. So y is a univariate random variable. Now, so if I apply Markov inequality on y, then probability y greater than lambda it should be less than equals to expectation of y upon lambda. And as this is
Okay, but as far as I know that we can apply the Markov inequality if y is a non-negative random variable, right?
I was coming to that. I mean, this is the sigma is a positive definite matrix, so any quadratic form will be always non-negative.
Yeah.
So now coming back to finding, so I think this will be the non-trivial upper bound. Now uh, to find the expectation of y,
Yeah.
I am taking the trace operator because y is a scalar. Now expectation of trace of x minus mu whole transpose sigma inverse x minus mu. Now, now I've forgotten it. Okay, okay, okay. I can take the this x minus mu part forward because trace of ABC is same as trace of CAB. Now, okay, now by the linearity of expectation, I can interchange trace and expectation. So I'm taking trace outside and expectation inside, then x minus mu into x minus mu transpose into sigma inverse. Now sigma inverse is a basically a constant term here. Uh, so I can take sigma inverse outside. I mean outside of the expectation, but not outside of the trace. So sigma inverse to expectation of x minus mu into x minus mu whole transpose. Now basically by definition, this is this matrix is sigma again. So this is sigma, and this matrix is sigma by definition. So now this is trace of identity matrix of order P. So this is P. So the bound should be p by lambda.
Good. Okay. Fine. Um, what do you mean by the estimability of linear models?
Now I cannot rewind at the spot of the moment, but
Okay, fine.
I mean,
Thank you.
if let's say if y equals to x beta plus epsilon is the Gauss Markov model, then beta curl is estimable. Anyway, a linear parametric function L prime beta is estimable if L prime belongs to the column space of X. I mean, it should be that, but
Yeah, okay.
for
Like you are most of 90% correct. Like actually, more easier would be that you can find a linear unbiased estimator L prime beta such that expected value of L prime beta is unbiased. Right. It gives the
okay, right,
parameter.
right, right.
Okay, fine. Uh, okay. Uh, can you prove this identity that you are aware of this multiple correlation, partial correlation part? Are you like comfortable with that?
Not that comfortable. And I mean, I know that, but not very much comfortable. Like, I mean, I can try.
Okay, so you know the notations that E1.23p all those notations.
Yeah, I know them. Know them.
So can you prove that the variance of E1.23p up to p is the error based on multiple is basically uh, determinant of sigma
This is equal to determinant of.
equal to determinant of sigma divided by the first partition term, that is sigma 1 1 of the capital sigma 1. All of them have the standard notation.
No, I think I have totally forgotten. No clue where to start. So I think I forgot everything.
Okay, okay, fine. So now, can you just state the Gauss Markov theorem?
Uh, Now in this setup, I mean, y equal to x beta curl plus epsilon curl. The uh,
Y- Yeah,
OLS estimators, ordinary least squares estimators of beta curl are the blue of, I mean, base linear unbiased estimator of beta. I mean, that is what
yeah.
Gauss-Markov states.
Now let me give you a, what should I say, like mm, a situation based question. Okay. So suppose there are two hospitals, A and B. Okay. And the surgery success rates for males and females are each higher in the hospital B. Like both the hospitals are conducting surgery for both males and females. But for both of the gender category, the success rate is higher in the hospital, say in hospital B. Okay,
I mean, for
here,
both male and female, right?
yeah,
Okay. Okay.
but
Mm. Okay.
okay, but the overall success rate is higher in A.
Okay. Okay. Is higher in case.
So, do you think that is it possible, or if not, explain. If yes, explain. I hope the question is clear.
Okay. Okay. I mean, every situation is possible or not, right?
Yeah.
Well, I think this is actually possible. I
Why?
mean, if I say the total, okay, let's say out of all male patients, uh, option hospital B has say 51% success rate and hospital A has 50% success rate, and out of all female patients, oh no, for both of them, hospital B has
Yeah.
more success rate, right? Okay, okay. Then I have to think again. I think this is not possible actually.
Okay. What if I tell you that if the size of the male and female group, okay, differ drastically, or if I tell you that hospital B may operate on more critical cases
Okay.
as compared to, like, think of real life situation. It may happen that hospital B has more critical surgery cases, so the
I mean,
success rate, yeah, is higher. But
uh,
if you compare with the hospital A, where the surgery rates are not that much critical, like if you take a real life example, hospital B takes surgery rates for the heart, all those kinds of bypass surgery or anything of that sort, which are more critical than if you just take hospital A as any kind of general hospital.
yeah, yeah. So
So it can happen, right?
yes, 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 it can happen. It can happen.
So this is a particular type of paradox. Are you aware of the name?
Simpsons paradox.
Simpson paradox.
Okay, okay, madam. At first, I thought that, but then I
Okay.
somewhat forward. Okay, okay.
And okay, so last question from my side, that is, uh, say you have a bivariate normal distribution. Okay.
Okay. Hmm.
So what is the distribution of the sample correlation coefficient? You can take a standard bivariate normal only, normal 0, 0, 1, 1.
Yeah. So, distribution of sample correlation coefficient.
Hmm. You can assume large sample.
I mean, this is R basically. So variance of small x comma y upon standard deviation of x into standard deviation of y. I mean, should I use delta theorem? I mean, using that.
If you use delta theorem, how can you come arriving at the distribution of R?
No, I mean, there's a result in that the the distribution of R using that.
Do
Let's
you
say,
remember that?
yeah, I
Like,
mean, R for I mean, for large sample setup, R approximately follows the normal distribution with mean population correlation coefficient, and the variance is, I mean, the variance would be, I think I should write it. Variance of R, I mean, asymptotic variance, right? 1 minus rho square times whole square by small n. I mean, I just know the result. I mean, I do not know the proof.
I am not asking. So okay. So yeah, I mean, like you went correctly. We will use delta method in this area. That's what I was seeing, whether you can identify the problem or not.
Okay.
Okay. So that's it from my side. So you can stop the screen share now.
Thank you, sir. Thank you. Close the whiteboard, right?
So, good afternoon, Rohan.
Good afternoon, sir.
You can open the slide here. Let us first of all solve a question.
Okay, okay, sir.
Simple statistic question based on conditional distribution. Say x1, x2, xn are IITs normal mu comma 1 variate. Parameter space for mu is real. Mu belongs to real number. And take n to be greater than 2, greater than equal to 2.
Okay.
It's very simple. You have solved this. I know. Compute a conditional distribution of x1 given x bar n. X bar n equals to small t.
Small t, right? Okay. It's one given is equal to small t. So, say, I
Can
mean,
you be much louder if possible?
okay, sir. Okay, okay.
Okay.
The in the probability that x1 given xn bar equals to t less than some small x. I mean, this will be the CDF of x1 given x bar,
Okay.
and if I subtract x bar from both the sides, I mean, yes,
Okay.
x bar here. Now, the distrib x1 minus x bar should follow normal mu comma 1 upon n, and I
It
mean,
will
sorry,
follow mu.
sorry. That was I going to correct. I mean, normal 0 comma 1 upon n.
0 comma 1 man, you're sure?
I mean, the variance 1 plus 1. No, the covariance is at 1 minus 1. Yeah,
Better you
yeah, yeah.
compute now. Variance of
I
x1
mean,
minus x1.
actually, yes. I should compute it. Yes.
When you are in the actual interview, better you compute. Don't write what you have remembered.
Go, sir. Now, variance of x1 is simply 1. Thus variance of x bar would be 1 upon n, because sigma square by n, and minus 2 into covariance of x1 comma x bar. Now, if I break the covariance as x1, then x1 comma x bar would be, I mean,
Only the x1, because xi is our ID. You are saying that only the x1 and x bar containing x1 will be there, and rest will be independent. Therefore, it will be zero. You're saying
yeah,
this.
right. So all of them
Okay.
will be zero.
Then
So this
it will become 1 plus 1 by n minus 2 by n.
minus 2 by n. So this would be
Okay.
1 minus 1 upon n. So minus 1 upon n. Now, this quantity is independent of x bar, because
x1 minus x bar and x bar are independent.
independent, right?
How can you
Because
say? Can you use some theorem which can relate to this x1 minus x bar and x bar are independent?
yeah, I mean, the both of them are normal distribution, and their joint distribution is bivariate normal. So I think I should show the covariance is zero actually. So
I know covariance you will certainly get zero, and you will compute say that x1 minus x bar and x bar will be zero. Can you state some theorem by which we can directly say that x1 minus x bar and x bar are independent? Can you
I mean,
recall some theorem?
for this setup, x1 minus x bar is independent of mu. So this is ancillary for mu, and
x1 minus
x
x bar is ancillary. Okay, great.
x bar is mu. For x bar follows normal mu comma 1 by n, and this
Okay.
is complete sufficient for mu. So by Basu's theorem, ancillary
Yes.
statistic and complete statistic are independent.
Yes. By Basu theorem, x1 minus x bar and x bar are independent. Now proceed.
Independent. Okay, so this thing is probability x1 minus x bar. Uh, Actually, there will be this will be less than, and x for that, for here I am replacing x bar as t. Now
Okay.
centering, this is again x1 minus x bar by the root variance, and now this thing is standard normal distribution. So
Hmm.
capital pi of x minus t into root over 1 minus 1 upon n, and
Okay. This is the distribution. Okay,
this
nice.
is the CDF,
Now,
right?
take a second question. Take the slide down.
Okay,
Suppose you have a statistic T.
yeah.
Now, T is both complete and ancillary.
Complete and ancillary.
T is both complete and ancillary.
Complete and ancillary. Okay. Yeah.
Uh, what is the ancillary statistic?
Uh, I mean, for a certain distribution with a parameter theta, if any statistic t has a distribution which parameters does not involve theta, which is independent of theta, then t is ancillary for theta.
Means probability distribution does not depend on parameter.
And, right, on theta, right, on parameter.
Okay. So you have been said that T is complete and ancillary. Can you find the distribution of T now? T is some statistic.
Okay, I mean, from for any distribution, I mean,
Yes, you have to find the distribution of T. It is
okay,
given
okay.
that T is complete and ancillary. You have to find the distribution of T.
I think T has a degenerate distribution at some point.
What?
T has a degenerate distribution at any point.
Achha, T is a DJ.
T,
It's a guess or you know how it is done.
no, no, it's a complete guess. I mean,
It's a complete guess is on the right direction, but you have to prove it. How it is coming degenerate.
Okay.
Well, you have been getting some intuitive idea in your mind that's why you said it's a degenerate distribution. Although it
Yes,
is a
yes.
guess, but you have been getting some intuitive idea. Try to proceed with that also.
I mean, let's say by definition of completeness, if expectation of t equals to 0, this implies that probability
It's the
t
expectation
equal
of
to
t equals to 0 or some h of t equals to 0, whereas h of t is a family of distribution. What is the definition of complete statistic?
right. Yeah. For any statistic t, if expectation of h of t is 0, that implies that probability h of t is 0 is equals to 1. That means
Right then, expectation of h of t is 0.
h of t is 0. Right.
H of t is a family of distribution for the statistic t, right?
Right.
That is what a completeness definition consists of.
Right.
So t is complete. You have written expectation of h of t 0, which implies probability of h of t of 0. Is this definition complete? I'm asking, are you not missing anything?
Right. For all theta, I mean,
For all theta belongs to parameter
the
space.
parameter space.
Okay.
For all theta, it should happen.
Now
Uh,
proceed. Now I have given you the hint. You have make a guess, and it is you have to reach to the degenerate part, right?
right.
Try to
I
reach
mean,
there. Now use the concept of ancillary.
okay. When I was thinking like that, for any distribution, the parameter space will vary from R, will vary in R. Now, if any statistic is ancillary for any value, then it should be degenerate. All must should be degenerate at some point, and it should be fixed. And so that was why
Okay.
saying that.
Okay. Let me give
Yeah,
you a hint. Take. It is given that T is ancillary. Uh, we can say that T is first order ancillary.
yeah. So
So then expectation of T is first order ancillary. मतलब, I am implying that if T is ancillary, it will imply that T is of first order ancillary. Okay.
yes.
Now expectation of T under some P, right? In the subscript of X E P. What is P? P is some family of models which belongs to capital P. P belongs to, for all P belongs to, right?
Capital P,
Expectation of T equals to C, some constant C.
some constituency, right. For all small p belongs to some capital P, right?
Uh, that P is some family of models.
Family of
Now this C is independent of P. This C is independent of P,
dependent of
family of models.
P. Right.
Okay. So P is the just underlying family we have.
Yes. So
Now try to proceed.
uh, now if we take h of t as simply t, then it is by the definition of completeness, this is coming out to be this 0, and this is so that means c should be 0, and for any kind of distribution, t must be degenerated at 0.
Can you, we can define h of t is equal to t minus c.
Right. So, oh, right, from that, right. So we define h of t as t minus c. Then from this statement, that probability h of t is equals to 0, the
And
1. Then probability
h is a function of t.
Right. Each is a function of P.
And now C is independent of the family. C is independent of P.
Right. So probability T of C equals to T equal to C is equals to 1. Now for any theta in any family. So Q
And
will
what
be
does C is equal to? We have to write C is equal to expectation of T under family P. You have to write all this also.
okay. So
Okay.
T is concentrated at the at its expectation, right?
Uh, Tell me, you know the Rao-Kramer lower bound?
Uh, CRLB, right? I mean, Kramer lower bound. Yeah.
Uh, you know Rao-Kramer lower bound?
Yes, sir. Yes.
Uh, it gives a lower bound. Okay. Does that bound guarantee that we have a sharp bound? Whatever the bound we get from CRLV,
Yeah.
is it a
I mean,
sharp? Means basically, I'm asking that you have. I'm giving a statement. Okay? You have to comment on this. A uniformly minimum variance estimator may exist without attaining Rao-Kramer bound. A UMU
uh,
estimator, write the statement. A UMVUE estimator may exist without attaining Rao-Kramer lower bound.
you are wrong. Okay.
What can you
Yeah,
say?
it is possible. I think it is possible.
It is possible.
Yeah.
Can you give an example?
So, that I have forgotten, but I think those estimators which does attends these lower bound are called uniformly minimum variance bounded estimator, right? I mean, and MVB, I think, and I have
Means
read that UMV.
variance of a UMB means you are saying the variance of a UMB estimator is greater than Rao-Kramer lower bound.
Yeah, I think it is possible.
Is it correct that variance of a UMB estimator is greater than Rao-Kramer lower bound? It may happen because Rao-Kramer lower bound says that it gives a lower bound.
Right. I mean, so the so maybe there might okay. I mean, it might not be possible also. There's maybe exists an estimator which variance is less than UMVB. No, that is not possible. But again, it is also not possible. So that is not possible. So UMV has the least variance, but
I'm asking, is there any possibility that the variance of the UMB estimator is greater than the Rao-Kramer lower bound? If yes, you have to prove it. If no, give an example.
okay, so I'm not sure. I mean, I have totally confused. I and I mean, I think it is possible, but I am not able to find any counter example.
Or- Because in many cases, the lower bound is smaller than the minimum variance attained by as any estimator. Among the class of we have we can say among the class of the unbiased estimators. So this means this directly means there is a possibility that the variance of a UMV estimator is greater than the Rao-Kramer lower bound.
Yeah. Right. Then it is possible, I think.
Okay, let me go through an example. You will be clear. Let's say you have to find the UMV of e to the power minus theta for an from a uh, random sample taken from a Poisson family with parameter theta.
Okay, x1, x2, xn. follows, Poisson distribution with parameter theta. Okay. So
You
okay,
know, you remember what is the UMB of e to the power minus theta?
so I mean I directly do not remember.
There are
I
many
think
methods to solve. One is to directly go with the Lemon Cephei, or you can compute with some probabilistic model taking balls n minus one balls like this. There are many methods to get the UMB of e to the power minus 2. Do you remember?
uh,
Okay,
minus
better you
two.
calculate. Better you calculate.
Okay. So I think I should use the equality of power series. I mean somewhat around that line.
Okay, okay. You can use the power set.
So summation xi is complete sufficient here, and now denoting it by t, and I am assuming gt is the UMVV. So expectation of g of t is e to the power minus theta. Now t also follows Poisson n theta,
Okay.
and so this is what should I write? I mean, small t equal to 0 to infinity g of t e to the power minus n theta t to the power n theta upon t factorial, and
It will be n theta to the power t, no?
right, not t to the power n theta, right? Yeah, flip those.
Don't use this kind of nuisance because it is expected that you can write
Okay.
this thing.
Yes, sir, yes, sir. And now now here I think again t equal to 0. So minus t to the power I think t should go to 0. So I think so I'm writing as n to the power t minus n to the power t upon t factorial. This is the expansion of e to the power minus theta.
It is an expansion. You are writing this here. Minus n to the power t.
Right. I mean, it should be minus 1 whole to the power t into n to the power t
You are writing expansion for e to the power minus theta.
minus theta.
Where does theta goes?
Into wait,
Write the expansion for e to the power x in the rightmost part first.
okay, e to the power x is summation x to the power n upon n factorial. So
Now you have replaced minus theta x with replaced with minus n, and you have to write the
okay, okay,
expansion for
okay, okay,
minus theta.
okay, right. It should be minus theta to the power. Okay, I am writing it clearly. So one will be minus 1 to the power t into theta to the power t upon t factorial. Now equating both the part like parts of theta to the power t and t factorial.
Okay, equate.
I mean, okay, I think e to the power. Okay. So there will be gt, but no, this side also contains theta. No, so this e to the power n theta, I think it should go this side. I mean, directly I cannot
Now you
expand
are
it.
doing because you cannot.
Okay, I mean, I temporarily
I was
forgot.
waiting when you will transfer e to the power minus n theta to right hand
Right.
side.
Right. Actually, this will not do it. So there, this will be n plus 1 into theta. And um, again, writing is here.
It will be minus of n plus 1.
Here it was e to the power minus n theta. So
It will be n minus 1 times theta. No? You are taking e to the power minus n theta to the right hand side.
okay, okay, right, okay, okay, right, right. E to the power minus n theta was there. Sorry. E to the power minus n minus 1 into theta. Now, so n minus 1 into theta to the power t upon t factorial. Now, now we can do that. I mean,
Now you can equate.
right now theta to the power t, I like first of theta to the power t, that gt into n to the power t equals to n minus 1 whole to the power t. So
You are equating the coefficients of theta to the power t by t factorial.
factorial, right?
Okay. Now gt
So
equals to n minus 1 by n whole to the power t,
whole to the power
where
t
t is summation xi, right?
is summation x, right? Yeah, yeah, yeah.
Now you have to compute the variance of this gt to get the idea that variance will be greater than or lower than the Rao-Kramer lower bound.
Okay, okay.
Okay. Now this is some gt. To help in the calculation part, let us say that consider this as some single random variable. Say it is y or z. Take z equal to n minus n to the power t,
Okay. So t,
and t
yeah,
is summation xi,
t is summation x, right?
which follows Poisson entity.
Is
Now
right.
compute variance of z.
Now, for variance of z, the expectation of z is known e to the power minus theta. So I'm
You
directly
don't need to compute expectation part because this
right.
will come e to the power minus theta.
I'm computing it to expectation of z square will be n minus 1 upon n. Sorry, sorry. Expectation of n minus 1 upon n to the power 2 into t. Now, this is where I need to stop. So, summation t equal to 0 to infinity n minus 1 upon n into 2t. Now, e to the power minus n theta into n theta whole to the power t by t factorial. Now, this thing I need to simplify. So, equal to 0 to infinity e to the power minus n theta. Now, uh, grouping the powers of t n theta into n minus 1 upon n whole square, this whole power t by t factorial. Now, I think I cancel out 1 n. Um, and now this thing is e to the power n theta into n minus 1 upon n theta square. So, yeah, this is the expectation of z square. So, variance of z will be this e to the power minus n theta into n theta into n minus 1 upon n whole square minus the expectation of t, which was e to the power minus theta. this thing squared. So again, I think I need to simplify this a little bit more.
Take e to the power minus 2 theta common.
Okay. Then
Take e to the power minus 2 theta common.
theta common.
Bracket. It will come e to the power theta by n minus 1. Okay. Calculation part you can skip. Now this is the
Okay.
variance of the UMB you got. Now you know Cramer lower bound for the Poisson distribution for theta.
Poisson distribution for theta.
You know the Cramer lower bound. What will be the Cramer lower bound?
For any
For
unbiased
the
estimator of,
Cramer lower bound for the variance of the unbiased estimator.
I mean,
E to the power minus theta.
E to G. Okay, okay.
We are talking about e to the power minus theta. No,
E to
sorry,
the power
I
minus theta, right?
completely skipped. It's going. I have to make you prove that variance of UMU
So
does
G
not
theta is
attain Cramer lower bound.
right, right, right. So G theta is E to the power minus theta. So G prime theta whole square will be, sorry, E to the power minus theta, then yes, theta, this thing square. So E to the power minus 2 theta. Uh, my twos are getting bad. And now the Fisher information, which is I theta. What is the Fisher information?
You are moving your head very down, and is there someone sitting besides you?
No, no, no.
Okay, I
I'm
theta will be theta by n.
theta by n, right? Okay, okay.
Now the Cramer lower bound will be
So CRLV would be G prime theta whole square upon I theta. So
it will be e to the power minus 2 theta into theta by n.
into theta by n. No, no, it is d G prime theta whole square by I theta, right? So n by theta, right?
Variance of t. What will be the lower bound of variance of t? Any unbiased estimator of g of theta.
Uh, G prime theta whole square by I theta. So G prime theta whole square is e to the power minus 2 theta.
I also okay. I have written you I theta equal to theta. I theta will be n by theta.
N
Sorry.
by theta, right? So that was theta n by theta. Okay, now it will be has CRLV will be e to the power
Now
minus 2.
compare both.
So this part is common, and now e to
Clearly,
the
e
power
to the power
minus.
minus 2 theta multiplied by e to the power theta by n minus 1 is greater than theta e to the power minus 2 theta by n.
Okay, so
Which one is greater?
I think this one e to the power theta by n minus 1 is greater
So
than theta by n.
so here we can see that UMB of e to the power minus theta does not attain Cramer lower bound.
Right, right, right. This does not attain CRLV.
Okay then, Rohan, thank you so much. You
Thank
can
you, sir.
now leave the meeting.
Okay. Sir, I have one thing to say. So
Be louder,
basically,
be louder.
this is off topic. So this technique of getting the UMVV using power series computation, I learned from you watching your videos. Thank you for that.
So this technique has you have learned from me only. Power technique.
Yes, power
Okay.
series computation
I,
techniques.
I, I have been practicing a lot during my graduation time with this technique only. And this is the better way to solve because in other way you can get also you cannot get also the right
Right, right,
thing
right,
that you are solving for. But in this it is a proper definition based, right?
right, right, right. Yes,
Because
yes,
it's lemon surface that expectation of h of t is some g of theta. We have to compute you. If
Right.
you are strong with the summation part, you can achieve that.
With that. So during my JAM preparation and seeing the solution of FLTs, you used to do that using these techniques. So
I
from there I
generally
learned it.
use this method unless exercise contains support of theta, then this method doesn't work.
This
Then
doesn't
you
work
have to
right.
do with the differentiating part and getting the solutions for that differentiating, whatever the equation we have.
Yeah, yes, sir. Yes, sir.
Okay.
So
Thank you so much, Ron. You can now leave.
thank you.